Welcome back, and we are going to do more trig and more integrals, but this time we're going to see an expression in an integrand that often involves a square root, and we're going to do a substitution, kind of like a u-sub, that involves a trig function. So this little table that I have shown on the screen here, square root of a squared, or square root of a squared minus x squared, right? And then the substitution that you should use in that case is x is equal to a over sine theta. These I don't like to say memorize, but yeah, you kind of have to memorize them. Okay. The other thing to keep in mind is we're going to be replacing x with each of these things. You have to replace dx for sure as well. But the other thing to bear in mind is that this is actually a right triangle in disguise. And so, for example, here, what we can do is say that if we rearrange this, solve for sine theta is equal to x over a, so that really means that when I'm using this substitution, I have a right triangle where if I take one of the acute angles as theta, right, I can say sine of that, which is opposite over adjacent, I'd have a triangle that looks something like this, right? And then maybe in the course of our evaluation, right, we could have a series of inverse trig functions, so we might actually need to know this other side, which is if we do the expression here, it would be a squared minus x squared. So that's kind of where that expression in the integrand comes from, because so we substitute it in there. We make the trig sub into the integral to make the arithmetic a little bit simpler in terms of the trigonometry. Okay, each of the other ones are just as important, but what I'm going to encourage you is whenever you do a trig substitution into an integrand, always have that right triangle at the ready so that you can use it to simplify trigonometric expressions at the end. We'll see it play out here, okay, in several examples. And just a reminder that you are introducing a variable theta, so your answer cannot contain theta or any trig functions that are a result of what you introduced. All right, lots of talking. Let's see some of this in action. All right, so first one, we have the square root of x, or 1 plus x squared dx, and if I look and compare that to the pattern, that's going to be our tangent, right? So we're going to use our tangent substitution first. Okay, so I'm going to let x be equal to a, which is 1 times tangent of theta, and that means that dx, I would substitute in secant squared of theta d theta. Okay? All right, I'll have to worry about the bounds too. I'll worry about those in just a moment. Let's do the integrand first. So square root 1 plus, and then it'd be tangent squared of theta, and then dx was the secant squared of theta d theta. Okay, bounds. Okay, these are bounds for x, so I have to sub them in. So 0 is equal to tangent. The only place that tangent is 0 is at 0. You could do inverse tangent of 0 and get that as well. And then if I put in 1 is equal to tangent theta. Tangent, so the angle where tangent is 1 is at pi over 4. Okay, and sometimes it doesn't hurt to show that work. So like 0 is equal to tangent theta. So then, theta is equal to 0. And similarly, 1 is equal to tangent theta. Pi over 4 is equal to theta. Okay, showing that work is always a good idea. All right, if I do this work though, okay, tangent squared of theta would be secant squared. Square root of secant. Squared is just secant. Okay, so then I end up with the integral from 0 to pi over 4 of secant cubed theta d theta. Okay, so that's fun. How in the world do we integrate this? Well, we have to do a little bit of work. Now you might be wondering, how in the world do we do this? Because we just saw in the last video how to integrate using secant and tangent if you had both of them present and odd exponents or both even exponents. Truthfully, this one, we have to use a different formula, a reduction formula, for secant, and so you'd have to look this one up. So this probably wouldn't be given to you on a gateway. I can't confirm or deny because I haven't seen that, but we'd have something of the form like, actually, let me back up. It would reduce to 1/2 tangent of x, secant of x, and then this piece you'd have to evaluate from 0 to power 4. And then plus 1/2 integral secant of x dx, and this would be from 0 to power 4. Okay, well, we still have to figure out how to integrate secant. That we can do. There's a special little, I don't like to say trick in math, but it is a trick in math. We're going to multiply this secant by secant of x plus I changed to x. My bad. Let's change these all back to thetas. Theta, 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 theta. And now this is secant of theta, tangent of theta over secant of theta plus tangent of theta. So I'm multiplying by 1. Okay. And the reason I do this is because if I imagine distributing now, right, so I'd have secant squared plus secant tangent, and then over secant tangent, what that actually ends up doing, I could do a u sub. Okay, I'm doing a lot of steps kind of mentally at once. You're welcome to verify it on your own. But if I do secant of theta plus tangent of theta as my u, and then du would be what? Secant squared plus secant times tangent, and then all d d theta. These are all thetas. Okay, so then that's the numerator, right? So this would be 1 over u du. Okay, so now I'll come back to this in just a minute. So it'd be plus, I'd have 1/2 integral, I'll fix the bounds in a moment. It'd be du over u inside. Bounds, let's see, secant of 0 is 1, plus tangent is 0. So that's 1. And then power 4, I get root 2, and then plus 1. So root 2 plus 1. Okay. And then here, if I put in power 4, let's see, that gives me 1 times square root 2. So it'd be square root 2 over 2, and then minus 0. Well, that just gives us 0. Okay. All right. So then I have square root 2 over 2 minus 1/2. That'd be minus 0. Plus 1/2, and then natural log of the absolute value of u evaluated from when u is equal to 1 to u is equal to 1 plus root 2. And so then my final answer here, square root 2 over 2 plus 1/2 times, and then I'd have natural log of 1 plus root 2. I can drop the absolute values because that's positive. And then natural log of 1 is 0, so I am done. Okay, so this one, yes, there was a little nuance, specifically this step. You'd have to look that up, okay, and that's fine. What I wanted to get in your brain at the beginning was the substitution with tangent, okay? Let's look at another. This one is maybe a little bit more useful to us. We have this whole thing, and then what I see is the 4 minus x squared, right? 4 minus x squared is a signal to me that I'm going to use this a sine of theta. Okay, so if it was 4 minus, a is going to be 2. So I'm going to use the substitution where x is equal to 2 sine theta. Then dx is going to be 4 cosine theta, d theta. Okay, so I'm going to substitute in. Dx was 4 cosine theta d theta over 4 sine squared theta, and then square root of 4 minus 4 sine theta. I'll write it out. 4 minus 4 sine theta, sine squared theta. Okay, so then those 4's are going to reduce. This under here is going to be a 2. So I'm going to have 1/2 pulled out all in front, and then that'll be, 1 minus sine squared is cosine squared. Square root of that is cosine. So then I end up with integral d theta over sine squared of theta. Okay, well that's just 1/2 integral cosecant squared theta d theta, and that is a nice antiderivative. That is just 1/2, negative 1/2 rather, of cotangent of theta plus c. And I'm done, right? No, I began in x, right? So then this is where I need to maybe reference my triangle. So I need to make a triangle, acute angle theta, and then x was, if I solved this, this would have been, x over 2 is equal to sine theta. So then x over 2, so then this is square root of 4 minus x squared. And cotangent now of this angle is adjacent over opposite. So this is equal to negative 1/2. And then adjacent was square root of 4 minus x squared all over x plus c. Okay, so this last step, that's where I have to use my triangle. Okay, to be able to rewrite it all back in terms of x. Okay. All right, last two examples, I'm not going to work them out fully. I'm just going to kind of get you started and then let you finish them. This one, as you look at it, the big thing to look out for is that square root of t squared minus 1 in the denominator. As you look at that, that should be a blinking red light for you to use a substitution where t is equal to secant of theta. Okay, and then dt would be secant of theta tangent theta d theta. Okay, so you can make that substitution. Okay, and then remember this is definite, so make sure to change the bounds and all that good stuff too. All right, next one is something that doesn't look incredibly helpful right now, but maybe we can do a little bit of playing with it. Okay, in particular, if we rearrange it, so integral x over square root, pull a negative out, x squared plus 2x minus 3 all dx. Okay, the x squared plus 1, or the x squared plus 2x, that could be a perfect square if I added 1, right? So let's rearrange that a little bit. Integral x over square root, and then I'd have x squared plus 2x plus 1 in here. That would be a perfect square. Negative out there, so that's actually a negative 1. So I'd have to add 1 back in, and then I'd have plus 3. Okay, so in all I'd have something like x plus 1 negative, this is underneath the square root, squared, plus 4. Okay, so rearranging that for just a little bit of clarity, it'd be 4 minus x plus 1 quantity squared dx. Oh, and then I can do like this as a u, right? So u is equal to x plus 1, du is equal to dx. Okay, what do I get after that? Integral, let's see, x would be just u minus 1 du over, and then square root of 4 minus u squared. Oh, okay, then that's actually easier. So now u is going to be right 2. Well, actually, I need to break it up even more. Just kidding. I need to break it into u du over square root of 4 minus u squared. And then the other one would be negative integral du over square root of 4 minus u squared. Okay, now this first one, the reason I had to break it up is because that is actually a u sub. Okay, denominator, or the stuff underneath the square root would be u, and then the second one, this is your trig sub with sine. Okay, so 2 sine theta, very similar to the one that we worked out. All right, so be careful on these. They might not seem like a trig sub right away. You might have to work on it a little bit and do some just plain old substitution in algebra.